you very much. Good afternoon, everyone. I hope you're feeling full now and ready to have some knowledge instead of some nutrition. I've called this talk HBC for Material Benefit, partly because I like play on words, but this follows on from a talk yesterday. You might remember, I think it was Alistair talking about power draw of various applications and showing that material science on Archer 2, for example, is taking typically 40 to 55% of the cycles and of the power. So I think it's a natural question to ask, is that actually good? Is that where we want to spend our time? Now, I'm in materials modeling, so I think I probably you don't even need me to say the answer to this. I'm obviously going to tell you that it is good. When I tell people at parties that I'm into modeling, I get some strange looks sometimes, but it's true. The answer really is because many problems that we face, technological problems but also societal problems, come down to materials problems. Sometimes it's the whole problem, sometimes it's part of the problem. So if we look at, for example, how we might produce electricity in the future, there's some obvious materials problems like solar cells, because the key bit of a solar cell is something that absorbs light, and you want something that absorbs as many wavelengths as possible and turns it into electricity as efficiently as possible. That's a materials problem. But you might also look at wind turbines and ask, how can we have light, strong wind turbines that can cope with high speeds, variable speeds, that don't crack, don't corrode, are easily machined? You might ask, if nuclear fusion is the energy, what do you make a reactor wall from? How do you cool the reactor wall? These are all materials problems. Now, when I say materials comes from the word matter. And actually, broadly speaking, it isn't necessarily what you would call a material. So cooling a tokamak reactor, it might be liquid lithium. Liquid lithium is not normally what you'd consider to be a material. I've done research on exoplanetary cores, on neutron stars, not what you conventionally have as a material. So really, I mean atoms. And specifically, usually, the electrons in the atoms. So the chemistry and the physical properties. Now, there's lots of different ways of doing this. There are two broad classes. There's what's often called classical force fields, which always has kind of shades of Star Trek when you say this. So this is where you assume that the forces on your atoms just depend on the locations of the atoms and maybe the chemical species. And that's it. And if you know what your material is, you know that it's got covalent bonds, for example, you can produce some very good force fields. If you want bonds to be able to form and break and change, then for many years that was not possible with force fields. There are now some what they call reactive force fields, but they're computationally more demanding. But at a sort of high level, classical force fields are for when you pretty much know what you've got. You want to know what it does over time, for example. So biosimulations, you know what the protein is, you know what the bonding is. You want to know, how does it change in time? How does it change in a water environment versus in vacuum, for example? How might it pack together? How might it respond to drug molecules? The main alternative class is first principles materials modeling, and this is modeling based on quantum mechanics, generally speaking. And this is more than an explanatory model, this is a predictive model. So this is now, by basing it on quantum mechanics, we think we can tell you what something does that's never, to our knowledge, even existed before, because we believe quantum mechanics is an accurate model of the underlying science. And there are lots of different flavors. There's quantum Monte Carlo, which is a bit similar to some of the lattice QCD stuff that was talked about yesterday. There's some a method called GW, and then there's probably the single most popular and compute-intensive method, which is density functional theory, known confusingly as DFT, even though the discrete Fourier transform is often called that too. So difficult to search for. And the three main codes on Archer that you'll see in alphabetical order, not in compute order, probably in reverse compute order, I don't know, is CASDEP, CP2K, and VASP. And that's mostly what I'm going to focus this talk on. So the aim of first principles modeling is to predict what a material does from first principles. In other words, start from the best theory we have and run it forward and see what happens. So I don't need to know if it's a semiconductor, if it's got covalent bonding, whatever. And this means that we can predict new materials with new properties. We don't need experimental input. That's the aspiration. Except when you need to make the thing, obviously. And as I said, that's because we can use quantum mechanics. And the whole point is that the properties are an emergent phenomenon. That's the idea. So this is my aspirational cartoon. The code I develop is called Hasnip. It's very similar to codes like VASP or Quantum Espresso or Abinit, and it's pretty similar to CP2K. The idea is that you would take some chemical elements and some atoms, and you'd put them in some configuration, and you would put in a model of quantum physics, and you'd give that to Hasnip, and Hasnip will tell you where the atoms want to go, where the low energy configuration is. It will tell you what the properties of that configuration are, and it will tell you how it will change over time. And really, this is the goal. And my job is to make this what actually happens. But at the moment, this is an aspiration. Why is it an aspiration? Well, one of the things, and why we're using the theory called density functional theory, because solving the actual Schrödinger equation is really, really difficult. And it's difficult because electrons are strongly correlated. So if I want to ask what's the chance of particle 1, electron 1 being at a certain point in space, it depends on the positions of all the other electrons in the system. And quantum mechanics is probabilistic, so it depends on all these probabilities. So if I needed, let's say I took 1,000 points in space, and said I'm only going to look at the probability of a particle in 1,000 points in space. For every one of those 1,000 points in space, I need to think about particle 2 being potentially at all those 1,000 points in space. And then for each pair of particle 1, particle 2, particle 3, 1,000 points in space. Every time I add a new particle, it gets 1,000 times more expensive. So if I start with something where even 1,000 points is rubbish, right? That's a 10 by 10 by 10 spatial grid. That's no space at all. And yet you quickly find within the space about 7 to 9 electrons, you're using the estimated 2021 global data storage. You're up to zettabytes for, let's say, 8 electrons. That's 1 atom of oxygen. Now, by anyone's definition, that's not a material. And we are not going to solve any problems with 1 atom of oxygen. What DFT does is show that there's a different system where the electrons, I've called them here non-interacting. You can think of them as not correlated. So I still have to compute maybe what's happening with the positions, but it doesn't depend on the other positions. So instead of multiplying the cost by 1,000 each particle, you just add the cost by 1,000 each particle. Now, of course, that gives the wrong answer if you literally do that. But there's a lovely theorem that says if you tweak the potential that they feel, you get the right answer. And that's what DFT is all about. There is an approximation involved in this tweak. There shouldn't be, but we don't know what the exact tweak is. But in principle, this is exact. But it transforms the cost from scaling like 1,000 to the n, or I've put exponential scaling here, to a polynomial. The conventional scaling is cubic. You can make it actually scale linearly, although with a high prefactor. Now that's what everybody's doing now. But as you all know, this is not, what we've been doing up to this point is not the future. The future, it has massive parallelism, and what we are parallelizing is changing, what we're parallelizing over. So we're moving from homogeneous to heterogeneous. Arguably, we've already moved. And we're moving from nodes of a couple of tens of cores and a few hundred nodes to nodes of hundreds, maybe thousands of cores, and thousands, tens of thousands of nodes, maybe more, who knows, plus accelerators. So one of the projects I'm involved with is an Excalibur project that Elizabeth talked a little bit about this morning. It's called the Particles at Exascale, or PAX. And it's a partnership between several of the high-end computing consortia, the collaborative computational programs, the UK Fluids Network, to really look at where we do similar kinds of operations, regardless of the science. So we're doing everything from the quantum that I'm involved with, up through the atomistic, up to particles used for coastal defences and structural engineering, through to a particle being a solar system for astrophysical simulations. So we're bridging something like 28 orders of magnitude in length and time. It's a bit insane. But it turns out that many of the computational kernels are really, really similar. In fact, one of the astrophysics codes, Swift, was an atomistic molecular dynamics program that they just co-opted and said, right, they're not actually atoms, they're stars. And the pairwise interaction is not electrostatic, it's gravitational, but it's still a 1 over distance squared form with some charges. So there are a lot of commonalities. It does, however, mean we've got 12 different codes. So it's lots of people. There are 11 RSEs just on this project, employed by this project, and of course many PIs, co-Is. The other thing that's probably has to be on any future HPC is machine learning. And really, I want to encourage you to think that this is an emerging software tool, just like we've got emerging hardware platforms, and needs to be part of the discussion. Even if the answer is, no, it's not appropriate, it needs to be considered. In the same way that I argue now, even accelerators are not something you can use. You need to think about it and to justify why they're not something you can use. Now, I've already mentioned CASTEP. CASTEP is the code I develop. It does density functional theory in what's called a plane wave basis. If you're familiar with plane waves, you'll know what this is. If you've used Quantum Espresso or VASP or ABINIT, you'll know that. If you're from a maths or a computing background, it might be more helpful to describe it as a three-dimensional Fourier basis. It's exactly the same thing. The plane wave Fourier basis is just a wiggly wave in 3D. That's it. And if there's a wiggly wave that way, and if I turn and look at this wiggly wave coming towards me, I get a planar front of intensity and then a dip, and so that's why it's called a plane wave. That's it. It's exactly the same. It's about 600,000 lines of modern Fortran plus MPI plus OpenMP. It needs some high-performance maths libraries. It needs an FFT library. FFTW is the one most people use, maybe MKL. And it's not technically open source because there's a commercial distribution as well, but it's free source code for, I've put academic here actually for non-commercial use. It doesn't have to be academic. Now, plane waves, they're a 3D Fourier basis, and at some point you ask the question, what do the electrons do at this point in the space we all live in, real space? And that means a Fourier transform, and that means all-to-all communications. So, in fact, an MPI all-to-all V is the workhorse here, as DK was talking about earlier today. The parallel distribution that we use, and pretty much all plane wave codes used, at least until relatively recently, was pioneered in the original version of CASTEP, actually CTEP, those of you old enough to remember the Cambridge-Edinburgh Total Energy Package, in the days when CASTEP and CTEP actually stood for something and weren't just a name. And it was designed in the 90s when we had 1, 2 core nodes and a dozen nodes. 2 dozen nodes was a big machine. You know, think back to, what would it be, the T3D, T3E, that kind of era, and it was fine. It was absolutely fine at that scale. That computing power is on a smartwatch now. This is not high-performance computing anymore, and solutions that were fine are no longer fine. They might be fine in the weak scaling regime, but increasingly what we're interested in is strong scaling, because calculations that used to be, oh, now I can work out where the atoms will go in the absolute lowest energy state. Now I want to know, how do I evolve that in time? So what used to be a groundbreaking simulation to go, where do the electrons even go? What are the bonds? And I used to use the whole of a large supercomputer to compute that. No, that's just one time step in my simulation now. That gets me 1 femtosecond. I want to simulate this for picoseconds, for nanoseconds, microseconds. I want to look at diffusion in battery electrolytes, fast ion conductors. You know, I want to design the next generation of things that we're going to use actually to revolutionize computing. So what we've done is we've really gone back to basics, and we said, what are we trying to do? We're trying to do a 3D fast Fourier transform. Our data pattern is a bit crazy. Our data pattern is we have a big FFT grid and 15/16 of it is 0. I haven't got time to go into why, but we have non-zero is in a sphere, a completely dense sphere in the middle of my grid, okay? So the traditional thing to do is to distribute the sphere, and that's it, and just worry about load balance. The FFTs are relatively short in any one dimension. Distribute 1D FFTs through my sphere, that's it. It's got us reasonably far over a couple of decades. It's not good enough now. But what we can do is we can look at other communities, for example engineering communities, where they've really worked at scaling FFTs because that's the whole of their workload. And they do things like process grids and optimizing the comms so you don't do an all-to-all, you do a restricted all-to-all in subgroups. And it's been generally considered that you can't do that in plane wave DFT because we have this crazy sparse, dense sparse pattern, if you see what I mean. We have a dense ball of data and then a load of zeros. But going back to it and just taking it all apart and looking at it again, we realize we can use those ideas. We just have to be cleverer. We just have to borrow ideas from load balancing, from communities that just do load balancing, for example, task scheduling. We have to go to people who just do the FFT, so these people who just do large spectral transforms, where if that doesn't scale, they don't scale. And by putting those together, we've come up with a new method that we've prototyped and are just now implementing in Castep, which gets significantly improved scaling. And actually, as we've implemented it, that's this pale blue line here, we've realized it's actually just better. You don't get so many gains on smaller process counts, but you never lose. It's just a better way of doing it. But critically, it starts winning and keeps scaling all the way across this. And I've stopped at 4,000 because we have 1,000 things to distribute over MPI, and I'm using 4 threads. So by 4,000, that is all the distribute. We have to distribute a different way to go beyond that. So this is giving you performance gains right the way across. Now, I'll just do one over that so you can see the speed, because it's always easy to pull the wool over people's eyes with it. Who knows whether that's good scaling or not. So here's the speed. This is how many iterations per second we get. These are the 2 ways you might do MPI and MPI and OpenMP, and this is the new method. It is not perfect. There is a lot of scope for optimizing this, but this is our first go at it, and we've had 30 years of optimizing the previous way, so I'm hopeful that we can make this a lot better. And it's not really Castep specific. So if this really works as we think it does, I hope it will be adopted by other plane wave codes. And you know, it's nice for me if Castep is the fastest, but actually it's better for everybody if everything improves. So our emphasis is on scaling, but it's faster across the board. And if you do the numbers on, say, 2,000 cores, it's 1.6 speed up. In other words, it takes 63% of the time. So we've saved 37% approximately of the energy budget, for example. Okay, there's a lot of nuance there, as discussed yesterday, but reasonably. So I'm going to put it to you that no discussion about power saving is complete without a discussion about how optimized your software is, including your communications. And just to show that this isn't a one-off, these are Castep optimizations over the last kind of decade that I've been involved with. I haven't led all of these, but I've been involved with them. This is for a small protein, well, a polypeptide in water, so it's a reasonably chunky calculation. And this was run on Hector and Archer, and I had to map the Hector ones. So there's a bit, the older ones are a little bit, I projected what they would be from Hector to Archer. I didn't always dig out the old code and make it build again. So there's a little bit of fuzziness. The blue line is time to science. So it's literally the electronic ground state, which has gone from a bit over 4 hours to about 35 minutes, just on software, with that caveat about me adjusting for what it would have taken on Hector. And I put the red curve as well because memory is a concern that I'm not kind of going to talk about, but we haven't put the effort into memory. And you can see that the on-node memory in the red curve has only got a factor of 2 improvement compared to about 8 in the parallel performance. And it's something we do need to address. Okay, I talked about GPUs. I'm just going to basically give an advert because we haven't got time to go into this. whenever I think about GPUs, I think back to the classic Seymour Cray quote about if I was wanting to plough a field, I'd rather have 2 strong oxen than 1,024 chickens. Okay, so that was Beowulf's rubbish, you want a big Cray chip. I mean, those days are gone, of course. And in a similar vein, I would like to suggest GPUs, at least if you think about the cores as CUDA cores, not real cores, it's like having a billion gnats. The peak performance is there, but getting all your gnats to all do a little bit of the job and pull in the right direction is challenging. But just like the chicken and oxen argument, the gnats are winning the argument. So it seems crazy, but it is the future, at least in the sort of medium term, until the CPU guys start bringing in, we get these hybrid things. But at the moment, a billion gnats hard to code, but the peak performance is outstanding and the performance per watt is also outstanding. So again, the future includes accelerators, and I think at least in the short term, specifically GPUs. And with HPC, we have to design for multi-GPU, multi-node. I don't think we can sit anymore with, oh yeah, it works on one V100 or one A100. We have to be more ambitious than that. And for codes that aren't there, and if looking at accelerators, I really encourage you and encourage you to encourage others to design this from the start because it's hard to retrofit. And we've tackled the hard problems for CPU parallelism, so let's not get lazy when we bring in GPUs. Castep was created in 12-person years, so 6 of us over 2 years, and that was 20 years ago. So there's a lot of investment in Castep. We don't want to throw that away and have a different GPU thing in Sickle, for example. We've got 2/3 of a million lines of Fortran that's working quite nicely on a CPU. So what we've done is we've restricted ourselves to the directives-based methods, OpenMP and OpenACC, and a lot of this is with Paul Collegia's team. And I'm just going to give you the headline results. This is on the Bead Tier 2 machines, so that's a Power 9 with V100 architecture. The node's 4 GPUs and 32 cores. We published a paper earlier this year with the first complete GPU port, as in it worked and it was faster. And we were very happy that we consistently got a factor of 2 speed up right across the board. And then we had a week's break, and then we thought, right, there's a few things we've been meaning to look at. Let's really look at them. And we looked at them, and having published this, we were slightly embarrassed to discover we can do significantly better with another 3 months of work. Now we've got the infrastructure in place, it turns out it's much more like traditional optimization now. With the added caveat that you have to worry about data movement, actually it gets easier. It gets much more like the conventional optimization we're used to. And if we plot the speed up, so obviously the CPU is 1, our published data is 2 and a bit, and now we can get consistently 5. So I do slightly wish we'd held off and done the publication. But anyway, and this 5 is growing now week by week. So we've actually got a mini hackathon in York next week.
Which GPU is that?
This is just a V100, but I should say this is comparing to Power 9. Which is not the leading CPU on the market. So I have done a quick benchmark of exactly this system on Archer 2, and Archer 2 gets you a factor of about 2 and a bit node for node. So if, let's say, halve all those speed ups compared to Archer. I mean, it's very difficult because it's also on NVLink, which you wouldn't necessarily get on an x86. There's a lot of nuance here. But apart from the nuance, this isn't PR, this is genuine across, well, I've only run about half a dozen benchmarks, but we haven't seen less than a speed up of 5 since we did those optimizations. Okay, we're on the home run now. So the last thing is the software stuff. There's an increasing desire to embed machine learning within simulations. Of course, people want to train ML on simulation output. That's not what I'm interested in. It's a great way to do some material science, but what I'm interested in is, can we use the machine learning inside a DFT simulation to accelerate it? So one way of doing this that we're looking at is, could I take a classical force field and then use a machine learning method to kind of learn the difference between the force field and the actual quantum mechanics and accelerate, say, a dynamical simulation or a structural optimization where I'm moving the atoms in the direction of the forces to get low energy. Can I do that on the fly? And of course, I probably can't do that blind. First of all, I need some steps to train it. And then probably I need to check, because I want DFT accuracy. There's no point throwing your accuracy away. And I also don't want uncertainty at the end. So I am going to do a final check. We ran this as an internship as part of one of the HECs. The UKCB HEC has 2 interns a year for over the institutions. And sorry, did I say 2? 4 interns over the year. We've had 2 students on this. We've had a final year undergraduate project, and we've had the summer internship. And what we found is you can get really quite impressive speed ups, but you do have to think a little bit about it. It's not yet as black box as we'd like it to be, but on a not particularly tuned example, if we check my ML every 5 iterations, so I'm doing a DFT, full DFT calculation every 5 steps, I get a total time to science reduction of factor of 2.3. I get a slightly better, so there's my speed up, I get a slightly better speed up per iteration. So the machine learning is not quite good enough. It costs you a few extra iterations. You get to the bottom of the machine learning energy landscape, and then the DFT goes, actually that's not quite the bottom. You need to, so there is a small extra iteration count, but it is offset by the speed per iteration. And as you increase the number of the gaps between doing your DFT, what you see is the speed up per iteration goes up quite significantly often. There's a little bit of noise depending on when you need to retrain. The speed up, it doesn't quite track that. And if you do the DFT even less often, you find that your speed up starts going down again because you end up going wrong too often. So there is a bit of a trade-off. But we can still reasonably achieve a speed up of 5 or 6 without working too hard, or rather the RSEs work hard, but without the user having to work too hard. This is reasonably black box for the user. Okay, we're pretty much out of time. I just want to say, I've talked about things that I understand and my users understand, at least if they come to our training workshop. Here's one thing that I mostly understand and I think most of our users have no clue about. We did an energy efficient computing study from the E3C initiative a few years ago with SDFC. Here's a capped nanotube. I turned it one way and I turned it the other way. What difference does it make to the physics? Nothing. I just defined my axes differently. That's literally all I did. Don't get the same performance in CASTEP because of how we decompose things. We do parallel decomposition along X. Okay? We don't do any auto-rotation. And yet, the peak memory performance doesn't really care that that's within noise. But the parallel efficiency that CASTEP tracks and reports, that's our estimate. If I line this along Z, the parallel efficiency is 5% greater. That's the estimate. If I actually do wall clock time, you discover it's 8% faster doing this completely mathematically equivalent thing with the same parallelism, just literally just tipping the domain, because it's an asymmetric domain, tipping it on one end makes a difference. This is a free 8% win if people were previously doing the wrong way or being pessimistic. This is an 8% loss not telling our users about it. Okay, I'm out of time, so I'll do just a whistle stop. So CASTEP is used. I started why we're doing materials, so I'll just give you, this is industrial applications. If you do a patent search just on Google Patents or whatever your favorite patent search is, which patent applications cite CASTEP? Just CASTEP, not VASP, not Quantum Espresso, not literally just CASTEP. You will very easily find rocket fuel, alloys, transistors, that sort of thing. Basically everything. Literally just one package, not DFT, not materials modeling. Okay, so what do we need? I would like to tell you that we need co-design, but we need co-design not to just be someone doing a tender talking to a hardware vendor or someone like me doing an application. We need co-design of the whole thing, including the funding mechanism, because we need the funding to work for us. We need there to be funded opportunities to do RSE long term. CASTEP is 20 years of work. And it's only been possible because it's been our hobby project. We've mostly been funded to do things with CASTEP, like sciencey stuff or other things. Or we've borrowed HEC funding and said, yeah, it's to support the whole consortium, but could you actually do this in CASTEP? Okay, so it's been sneakily funded. This year we got a Software for Research Communities grant. So we've got 3 years of CASTEP funding for only the second time ever. First time for the core code. We need machines to run and to develop on that you can actually debug on and profile and optimize on and not wait a day to do it, which is a big problem for GPUs, multi-node GPUs. We need people to design and implement the methods. We need users to do the research. We need training to give us the skills. And we need education so that people understand in a broader context that this is good stuff. It's a good use of taxpayers' money. It's a good career for school kids to come into. And that spells compute. So with that, I will say we need more compute. Thank you very much for your attention.